To most of us, rain is just rain, right? But if you're an engineer, it's a completely different story. Not all rain is created equal. Understanding the type of storm, the actual physics happening up in the clouds is absolutely critical. Why? Because everything from a bridge to a dam to the drain on your street is designed based on the kind of rain it's built to handle. So let's just dive right into that. Why does it matter? A sudden flash flood versus a week-long drizzle. What's the big deal for an engineer? Well, the answer is pretty much the difference between a city that works and one that faces a catastrophe. And in this explainer, we're going to break down exactly why. Just look at this massive dam. Every single piece of infrastructure you see out there, big or small, is the result of some really critical calculations. Engineers have to ask themselves, what kind of water is this thing going to face? And the answer to that question starts with understanding the storm itself. So here's what we're going to cover. First, we'll whip up the basic recipe for any kind of rain. Then we'll zoom in on the one critical ingredient that really changes things up. After that, we'll get into a tale of two very different storms. And finally, we'll see the payoff, how all this knowledge actually keeps us safe. All right, first things first. Before we can get into the different types of rain, we really have to get a handle on how rain forms at all. And honestly, the basic recipe is way simpler than you'd think. So, at its most basic level, precipitation is just water, right? It could be liquid, it could be solid, rain, snow, hail, all just falling from the sky thanks to gravity. But for an engineer, this isn't just weather. This is raw data. This is the starting point for every single design. Okay, so for any of that water to actually fall, you need three key ingredients to come together. It's kind of like a recipe, and if you miss one step, the whole thing fails. First, you need your raw material, that's water vapor just hanging out in the air. Second, that air needs to get pushed upwards, which makes it cool down to its dew point. That's the magic temperature where the vapor turns back into tiny liquid droplets. And third, those little cloud droplets have to bump into each other and grow until they're heavy enough to actually fall. No exceptions. Now, of those three ingredients, the one that really defines the personality of a storm, if you will, is that second step, uplift. The way the air gets forced upwards is what separates a short, violent thunderstorm from a long, drawn-out, drizzly mess. And there are basically three ways this can happen. There's convectional uplift. Think about the sun just baking the ground on a hot day, causing a pocket of air to shoot straight up. Then there's orographic, which is just a fancy way of saying the air hits a mountain and has nowhere to go but up. And finally, you have cyclonic uplift, which happens when these huge masses of warm and cold air crash into each other. Now, they're all important, but for engineers, two of them, convectional and cyclonic, create the most different and the most challenging problems. So that's what we're going to focus on. Okay, so let's put these two storm types head to head. I mean, sure, they both make rain, but to a hydrologist, they are completely different beasts, and they have completely different consequences on the ground. And wow, when you put them side by side, you really see just how different they are. They're polar opposites, really. A convectional storm is like a quick, vertical punch of air over a really small area. It's over in a few hours tops, but it is incredibly intense. A cyclonic storm, the exact opposite. It's a slow, gentle lift of air over a massive region, sometimes lasting for days, but at a much, much lower intensity. This really says it all, doesn't it? Convectional storms are hit-and-run events. They're focused, they're violent, and they're gone in a flash. You can literally have a torrential downpour on one side of a city while the other side is completely bone dry. And this right here, this is probably the most critical difference for an engineer. Intensity. That's just how fast the water is hitting the ground. And as you can see, the intensity of a convectional storm is just off the charts compared to a cyclonic one. And that super high intensity is exactly what overwhelms drainage systems and causes those really dangerous flash floods. Okay, so this brings us to the big payoff. How does all this weather science actually translate into things we can see and touch? Well, it's all about building stuff that doesn't get washed away. This is really the bottom line. An engineer can't just design for rain. They have to design for a very specific type of storm, because each one throws a completely unique challenge at them. So you've got your convectional storm, high intensity, small area. That's your classic recipe for an urban flash flood. But then you have the cyclonic storm, low intensity, but over a huge area and for a really long time. That's the main worry for something massive, like an entire river basin where the total volume of water is the biggest problem. And this is where it all clicks into place. To handle those convectional, hit-and-run storms, you need small-scale stuff that can take a sudden, massive punch of water. We're talking about city storm drains and culverts.
But if you're managing a whole region, you're designing for those cyclonic storms. You're thinking about huge dams and planning how reservoirs will handle a slow, steady stream of water coming in for days on end.
So, when you boil it all down, it's pretty incredible. By understanding the physics of how air rises in the atmosphere, we can actually predict how a storm is going to behave. And by predicting its behavior, we can design and build the exact right infrastructure to manage the water and keep all of us safe. And all of this leaves us with one pretty big and pretty urgent question for the future. All of our infrastructure, our cities, our dams, our bridges, it's all designed based on the storms of the past. So if the storm dictates the design, what happens when the storms themselves start to change? It's a critical question we all need to be thinking about. Have you ever really thought about what it means when the forecast says we're getting an inch of rain? It sounds so simple, right? But the actual science of counting raindrops to measure a storm, well, it's a way more fascinating and high-stakes challenge than you might think. Let's dive in.
Okay, get this. For a lot of places on Earth, more than half of the entire year's rainfall comes down in less than 15 days. That's a massive, massive amount of water in a super short window of time. So yeah, measuring these storms accurately isn't just some neat science project. It's absolutely critical for survival.
So if rain is this wild, concentrated, and kind of chaotic thing, how in the world do we even begin to measure it? How do scientists turn a crazy downpour into reliable data that, helps keep our cities from flooding and our farms growing? That's really the big question we're going to tackle. All right, first things first, you got to understand that not all rain is created equal. Before we can even touch on the how of measurement, we have to get our heads around the sheer wild variability of it all. This is the first major hurdle. And this really puts it all into perspective. Just take one country, India. In the desert regions out west, they might get only 10 centimeters of rain for the whole year. But then you travel over to the mountains in the northeast, and you're looking at over 1,100 centimeters. That's 100 times more rain. So how can one system possibly work for such insane extremes? So with that massive variation burned into our minds, where do we even start? Let's get down to the fundamental tools and the core principles, the actual art of measurement itself. The basic unit for everything is something called precipitation depth. It sounds technical, but the idea is actually brilliant and simple. When you hear 1 centimeter of rain, just imagine that rain falling on a perfectly flat surface, like a giant parking lot, with nowhere for the water to go. No runoff, no soaking in. The water level would be exactly 1 centimeter high. It's just a standard way to talk about the sheer volume of water that fell. And the classic tool for measuring that depth is the good old non-recording rain gauge. Honestly, you can just think of it as a very, very precise bucket. A great example is the Siemens gauge, which has been a workhorse in India for years. It's got a funnel that catches the rain and channels it into a measuring tube. Deceptively simple, but it really, really works. But here's the thing, having the right tool is only half the battle. Where you put it is just as crucial. There are some really strict rules about this. First, you need level, open ground. Second, there's a height sweet spot. It has to be high enough so rain doesn't splash in from the ground, but low enough that strong winds don't blow over the opening and mess up the reading. And the golden rule? Any obstacle nearby, like a tree or a building, has to be at least twice its height away from the gauge. It's all about getting a pure, unobstructed sample of what's falling from the sky. Now, that simple bucket is great for telling you the total amount of rain you got. But what if you want to know the story of the storm? Like, when did it start? How hard did it rain? When was the peak? For that, you've got to level up to a more advanced tool, the recording gauge. And this right here is the key difference. A non-recording gauge gives you one number, the total. A recording gauge, on the other hand, gives you a narrative. It's literally creating a plot of rainfall over time, so you can see the intensity. Was it a light drizzle or a total downpour? And exactly how long it lasted. This is the kind of data you really need to analyze a storm. And there are some pretty clever ways these things work. The tipping bucket gauge has this tiny seesaw inside that tips back and forth every time a very small, precise amount of rain collects, and each tip sends an electrical signal. The weighing type is exactly what it sounds like. It just continuously weighs the water as it collects. And then there's the natural siphon gauge, which is this old-school mechanical marvel with a float that rises with the water, drawing a line on a chart, and then automatically siphons itself empty to start the process all over again. Pretty cool, right? Okay, so we figured out how to measure rain at one single spot. But a storm isn't a single point. It can be hundreds of kilometers wide. There's no way one gauge can capture all of that. So to really understand a storm, we have to zoom out from that single point and see the whole picture. And this leads us to a fundamental principle in hydrology. To get a good representative picture, you need as many rain gauges as possible. You have to build a network. The more dots you have on the map, the more accurate your image of the storm is going to be. So how dense does that network need to be? Well, the World Meteorological Organization, the WMO, has guidelines, and it all comes down to the terrain. In big flat regions, one gauge every 600 to 900 square kilometers might be enough. But in the mountains, where the weather can change in a heartbeat from one valley to the next, you need a much tighter grid, like one station for every 250 square kilometers. Context is everything. A network of gauges is a huge step up, but you're still just connecting the dots. There are always gaps. But what if you could see everything in between those dots? What if you could get a continuous, real-time map of the entire storm from one spot? We'll say hello to meteorological radar, the ultimate super gauge. Here's the basic idea. A radar dish sends out a beam of energy. When that beam hits raindrops, it scatters, and a tiny bit of that energy bounces back to the dish. That's the echo. Now here's the magic part. The strength of that echo tells you about the size and number of the raindrops. A stronger echo means heavier rain. So by scanning the sky, the radar can literally build a detailed live map of the storm. So we've gone from simple buckets all the way to advanced radar theory. Now let's see how this all comes together in the real world. We're going to take a look at a fantastic case study, Zimbabwe. First, let's just set the scene. This chart shows that Zimbabwe gets about 650 millimeters of rain a year on average. That's quite a bit less than the world average, and way less than a monsoon-heavy country like India. So when water's a more limited resource, measuring every drop becomes incredibly important. And this is where those WMO rules we talked about become so critical. Hydrologists in Zimbabwe don't just use a one-size-fits-all approach. They tailor the network to the land. In the rainy, mountainous highlands, they pack the gauges in tight. In the flatter central regions, they use the standard density. And out in the really dry lowlands, they can get away with a much sparser network. It's just a smart, efficient use of resources, all based on solid science. They're also really strategic about the specific technology they use. In those huge, remote parts of the country, the tipping bucket gauge is the perfect tool. Remember that little seesaw? Every tip generates a digital signal that can be transmitted automatically by satellite or radio. This is a total game changer. It means you can get critical, real-time data from the top of a mountain without ever having to send a person up there to check it. So, from the humble bucket to the all-seeing eye of radar, that's the science of measuring a storm. But this isn't just about collecting numbers. This is about managing our most vital resource. This data is our first line of defense against both devastating floods and crippling droughts. Which brings us to a final, really crucial question. What happens if we get it wrong? What's the real cost of a bad measurement?